Thank you very much, and I would like to start by thanking the organizers and especially Gediminas for inviting me here to this beautiful city. In fact, it's my first time not only in a Baltic state, but also in a former Soviet Union state. Although I'm from a former Soviet bloc country, I've never been to a former Soviet Union country. I'm going to talk about some quantum control that we have done recently on IBM Quantum. I must warn you that I'm a theorist, and I'm going to tell you about experiments that we have done on our own. So it's like 5-year-old playing with fire. It's very exciting, but you can easily run into trouble. And we found out actually that what's the difference between experimental life and theory life. I'm going actually to speak not only about experiments on IBM Quantum, but demonstration of some of the control techniques on other media like trapped ions and doped solids, which were done in collaboration with some groups in Germany, UK, and Sweden. This is the overview of the talk. First about a very powerful control method, composite pulses. Then a little bit about dynamical decoupling, and then about a new phenomenon that we discovered, power narrowing, which is something that contradicts basic notions in spectroscopy. First of all, what is composite pulse? There are a couple of experts, probably a few more here, that know what they are, but most of you probably don't know. A composite pulse is actually a train of pulses with well-defined relative phases, and these phases are control parameters which are used to shape the excitation profile of our qubit or qubit or qubit in any desired manner. And it turns out that they have properties that are basically not present in any other control technique. Now a little comparison of basic structure of excitation of qubit. We of course all know the resonant excitation, which follows the sine square of 1/2 of the pulse area. We have adiabatic evolution, which is very stable, but you can never reach actually perfect fidelity with adiabatic process. And then you have composite profile, which is very flat here and essentially at zero error. So I'm going to speak about composite pulses in the beginning. And this is the profiles you can expect with composite pulses. You can have very well-defined pi pulse here with zero error essentially at great sensitivity to variations in the parameters. You can, however, squeeze the excitation profile. Here you see the blue curve within the Rabi oscillation. I'll show results and some interesting prospects of this case, which is much overlooked. You can have passband when you are flat here and also there in the bottom, and you can have half pi pulses. So actually at any probability you can lock the transition probability basically at will. A little history of composite pulses. They come from nuclear magnetic resonance from the 80s. We were surprised, and also actually some people from NMR that we talked to, that in polarization optics already in the 40s they knew the idea and the concept, and there is formal mathematical equivalence between the Schrödinger equation and the respective equations in polarization optics. And in quantum optics they were introduced, as far as I know, in ions. And here I'm quite glad to see Rainer Blatt sitting in front, because I think you were the first who used them, and I think they were one of the enabling methods that allowed to publish a number of landmark results in well-known papers. Another person from the ions community was Christoph Wunderlich, who also had a series of papers a little later using composite pulses. What we did different from, because the field is really crowded with people from NMR and also from quantum optics, was to use a different approach. Actually, the block vector approach and the block vector picture is standard way of derivation in NMR, and there they only draw block sphere and block vector moving around. This is equivalent actually to use a simple SU2 method. And when the propagator is described by two Cayley-Klein parameters A and B, complex valued. And it turns out that it's very easy actually to use this approach, because the overall propagator, which is a product of the individual propagator with the different phases inside, turns out that are much more preferable for the computers. The computers seem to prefer much more to work with complex matrices 2x2 than real matrices 3x3. Just very quickly, you can find solutions that are impossible or not known in NMR. Now, broadband composite pulses are the most obvious applications because they give great robustness to experimental errors. We were able to derive a sequence of composite pulses with this phase. You see this is analytic expression, and in fact you can have infinitely long composite pulse. You see here the Rabi oscillation, which quickly is flattened already by 3 pulses, and we have up to 45 you can draw, but we can go further. And this is in the deviation in logarithmic scale. This is a single pulse. You have very little room for deviation, but with composite pulse you can quickly go very quickly. And this is the level 10 to minus 4 error. You see already with 3 component composite pulse you can be very robust to errors, more than 10%. The first experimental demonstration actually of our sequences that we derived was done in doped solids by the group of Thomas Halfman in Darmstadt. They have sort of atoms, the praseodymium 3+ ions in this crystal, which is impossible to pronounce. The real name looks like this, and they did composite pulses in this transition. Actually, this was experiment in light storage. They need to rephase coherence in light storage, and we heard this morning and afternoon some talks about polaritons and light storage. And this is the single pulse, 3 pulse, 5 pulse. You see that the efficiency goes up and also broadens as a function of the pulse duration, which is essentially the pulse area. Then we had some joint work with Winnie Hensinger in Sussex in ytterbium 171, but ion, not atoms, that we heard in the previous talk. And you see the effect of from a single pulse to a composite pulse. The experiment in particular created equal superposition of these two states starting from this one. Then we had a joint paper with the group of Christian Ospelkaus in Hanover, and you see the effect of composite pulses here. This is the effect of actually Hadamard gate or half pi pulse, how it flattens, and you know the Rabi oscillation just goes quickly through this point. Now we are very happy to collaborate actually with experimental people and many good friends around in Europe, but of course it's very thrilling to try yourself to do it. And IBM really did something that is, in my opinion, game-changing. They offered open access to their quantum processors, especially to the one currently with 5 and 7 qubits, and you have to pay not much actually for the other ones. So I think now every theorist who does quantum control and quantum computing and also quantum sensing now has the opportunity to prove the beautiful theories on the open access IBM Quantum on the cloud. And our ultimate objective there is actually to create perfect gates, because we found out that the gates provided by IBM are not always perfect, and the gates on one qubit are different from the gates on another qubit, etc., etc. So this is our ultimate gate, to create, using quantum control methods, perfect gates, and then use them to build quantum circuits. Now there are two approaches actually to IBM. There is a front end and there is back end. In the front end, I'm just explaining, maybe for some people it will be trivial, but in the front end it's drag and drop gates that are prepared by IBM. They are supplied by them and you can build your quantum circuit. But they give you access also to the back end, and the back end you have full control of the microwave field. The shape, the carrier frequency, the amplitude, the duration, the chirp, everything. And people in quantum control, this is a dream actually. They give you the field, you can do anything with it. And this is what we did. Now this was the first demonstration already 3 years ago of a broadband composite pulses. This is theory and this is experiment, and you see it's quite perfect. Here this is the readout error, that's why it doesn't reach 1. And this was published actually last year with a co-worker of mine. And another very interesting concepts are the so-called universal composite pulses, and we've talked to some people in NMR. They were quite fascinated by them. They were discovered by us in 2014 and demonstrated in doped solids. What is special about them is that they compensate any experimental errors, as long as these are coherent errors. This means pulse duration, pulse amplitude, detuning, chirp, anything. And this is the performance of a single pulse as a function of the detuning and duration, essentially the Rabi frequency. And you see here the red spot. It's very small red spot. This is 10 to minus 4. And when you go to 3, 5, 7, 9, all the way to 25, you see big red islands where the error is less than 10 to minus 4. Really very interesting pulses. They were demonstrated in doped solids, but these are results from IBM. And this is experiment and this is theory. This is single pulse, and here signal pulse, 3 pulses, 5 pulse type A, 5 pulse type A, 5 pulse type B, etc. And you can find really great similarity between experimental theory. Actually, this was at some occasions even scary, so I had to check, because this was my collaborators and students, they did it. Because at IBM they also have simulator, and I was worried at some time that might be using the simulator. They look really good. Now, narrowband composite pulses are something that are overlooked, but they're also very powerful control method. This is the usual radio oscillation here, the black, and you can squeeze the excitation profile. You see here, this is almost a delta function. These are the phases of composite pulses that we discovered some more than 10 years ago. This is the phases of the pulses, and this is analytical formula for the phases and a few examples of them. And this is how transition probability looks like for this narrowband composite pulses. It's the power of sine, and when the number of pulses grows, obviously the sine squeezes very quickly. And this has a number of applications, actually. I was quite thrilled this morning to hear from Eugene Demler's talk about quantum pointillism. Never heard about it, but with narrowband composite pulses, you can really localize excitation in space, basically indefinitely, in the perfect world of theoretical physics, of course. And with trapped ions, you can have a Gaussian spatial profile of your laser beam, but you can squeeze the effect so that you can kill the crosstalk here to the neighbors. If you want to address this one, the neighbors see some residual unwanted field, and with narrowband pulses, you can actually kill the crosstalk. This is still on paper, something on paper. And we did some simulations in collaboration with the doped solid group in Darmstadt. This is the profile of a single Gaussian pulse in space. Now this is space here in both directions. And with narrowband pulses, you can see that you can squeeze not the beam itself, but the effect on the ions in the doped solid to basically a spot. And this is a factor of nearly 18. Now we learned that theoretical physics is different from experimental. As they say in theory, theory and practice are the same, but in practice they are not. They managed to find squeezing, but it was not a factor of 18, but a factor of 3, although there are new results which show much better squeezing, and on paper, we already have on paper, on theory, already a squeezing factor of 50, which means if you have 1 micrometer spatial diameter of your beam, you can squeeze the effect to 10 nanometers, which is quite remarkable, I think. This is work in progress. Now another work, this time with Stockholm, was about thermometry of trapped ions. So these are the two qubit states of a trapped ion, and they, in the quantum regime, they are addressed with phonons, with 0 phonon, 1 phonon, 2 phonon, and so on. The lower state and the upper state. And in the lump decay regime, this coupling depends actually on the number of phonons. And because narrowband composite pulses can really discriminate different pulse areas, it means they can discriminate different couplings. And now if we have thermal distribution, this will be the populations in a thermal ensemble with n average equal to 1. And just applying narrowband composite pulse and moving its, for example, amplitude, this will be the profile coming from the population of the 1 phonon state, the 0 phonon state, 1 phonon state, 2 phonon state, and so on. And this is the profile that is expected to be observed for thermal distribution. And if you invert the pulse area, this is A to -2, they actually become equidistant. And this is what one can achieve with narrowband composite pulses. Really measure the phonon state 1 by 1. I know there are other methods, but they use superposition of Rabi oscillations, because each of these state will give rise to Rabi oscillations, and they will superimpose, and then they run numerical methods actually to find the populations. Now if you have a thermal distribution, of course it's much simpler to measure n average by using red and blue sideband, and when you take the ratio of the two signals, it gives directly an average. But if you have a non-thermal distribution, you can really use this method to measure them 1 by 1. And this is an experimental slide from Marcus Henry's group. What they did here, they prepared some Fock state, and here is the initial Fock state on the vertical axis, and there is what was measured using narrowband composite pulses. And the diagonal picture here indicates that what was measured is what was prepared. And the difference between the different frames is the number of composite components in the composite pulse. This is for 15 pulses. This is work in progress. And this is demonstration of narrowband pulses in IBM quantum theory and experiment. You see they're quite similar. And here we have this profile. The orange profile is from 1001 pulses. And so far in NMR, the largest number of composite sequence was actually 81. We were quite surprised to see that this feature survives here, which means also, by the way, the qubits at IBM quantum are quite good. And we have some, for example, fractional excitation. You see here different level. You can lock the population. You can have passband profiles when you are flat here and there. And you can have here narrowband fractional pi, and you can have passband fractional pi, and you can play a lot. Now a little bit about dynamical decoupling, but maybe I should jump over because I see my time. I have, but I prefer to, okay, maybe a little bit, but then it's not me to blame. Now dynamical decoupling is dynamical decoupling is, of course, basic method in quantum control, and it originates from the papers by this gentleman, first Han Echo, Carr, Purcell, Mabel, Gim, and dynamical decoupling has the objective to produce unit propagator. You have a quantum system in a particular state here, we let it evolve, and we want to find it in the same state after a while. And this is especially a big problem if you have inhomogeneous ensemble, and we apply pulses, pi pulses in between, so that in the end we want to have unit propagator. We have nothing to happen to the system. And this is the classical thing is the CPMG sequence, which is repeated to CPMG2, and you can have thousands of pulses. And very popular one is XY, when you have 4 pulses repeated over time, and these two are shifted by phase pi over 2. Now, because we were so overwhelmed with composite pulses, we decided to put phases on these pulses, on these pi pulses, and see what happens. And actually we derived new composite sequences, which were called universally rephasing sequence, UR. Here they're called UDD, but later on we call them UR. And they were published in this paper in PRL 2017 and demonstrated in doped solid to perform very well. And we found analytical formula again using the SU2 approach, where you can have arbitrarily long such sequences. And these are examples of the 6 and 10 dynamical decoupling sequence. But again, here it's not the objective to produce some fancy excitation profile. Here the objective actually is to produce the unit propagator. Of course, if you do nothing, your system may be subjected to some residual magnetic or electric field and it will accumulate wrong phase. So we want to kill this sort of effects that when we don't apply external field exist anyway. These are experiments from Darmstadt. This is theory prediction and this is experiment, and you see this is CPMG, which is known to be not optimal. We were quite surprised that XY4 didn't perform well. KDD is one of the best there, and KDD in X4 didn't perform as expected. But these are the universally rephasing UR sequences, and you see that they easily outperform this here. And last year, I think it was last year or this year, the group of Dani Lidar made on IBM Quantum, it was not us, but him, extensive comparison of various dynamical decoupling sequences, and you see here UR10 compares, this is the error here, to QDD, which was derived by them. So these two they claim were the best, and you see here the architecture of a 7-qubit quantum processor at IBM. Quite disappointingly, one of the most popular one here also didn't perform well, XY4. And this is comparison of various of our sequences demonstrated by Dani Lidar, and you see all of them perform actually quite well. So we were very pleased. They actually overtook us. We also had some experiments on the same, but they didn't perform as well as we expected, and we were looking where the error was, and then their paper appeared. But we have newer sequences which promise actually to be better even than these ones. Now the effect of power narrowing, which is probably unusual, because the usual thing is power broadening, and this is found in all spectroscopy textbooks. If we have CW excitation, and this is the signal that comes out of our two-level atom, This is time average 1 over t of rho to 2, integral from 0 to t. And this is the profile that you get. Gamma is the natural line width, omega is the Rabi frequency, and delta is the detuning. And when you plot to this line, this is the value of the Rabi frequency. When it's gamma, it's sort of narrow, and that's why in spectroscopy they take as little intensity of the field as possible in order to do the proper spectroscopy. And you see how it broadens very quickly when the Rabi frequency grows. This picture, actually, I don't know where it is from. I just downloaded the picture from the internet, and the first that showed up, and you see typical power broadening. So power broadening is the paradigm in spectroscopy. Now at IBM, we knew from before, I'll show you another slide, that rectangular pulses, when you have a rectangular pulse, it shows typical power broadening. This means linear power broadening. And this is simulation, this is a result from IBM Quantum. This is the tuning here, and this is the Rabi frequency. And we see that when you increase the Rabi frequency, this feature here, which is for a pi pulse, quickly spreads up and becomes broadened quite a bit. This is an experimental result, and this is the red one for single pulse, then for pi pulse, then for 3 pi, 5 pi, and so on up to 9 pi. You see clear broadening of the line for rectangular pulse. This is very essential. And this is when we plot as a function of the Rabi frequency. A characteristic feature of the rectangular pulse is the increase of the oscillations with the Rabi frequency amplitude. This means taking here is for some detuning. Taking here a line, a section, and when you plot as when we vary the Rabi frequency vertically and plot the population, obviously this we see oscillations with increasing amplitude. Very characteristic of power broadening is also this picture, although it's not like this. Power broadening is associated with probability plotted versus the detuning. And now there is a very easy explanation actually of power narrowing. At the time, this was 10 years ago, with a student of mine, we published a paper in optics communications because it was actually rejected from physical review. They said this is impossible, but what is power narrowing? There is power broadening only. People in optics communications, the referees, were more receptive to new ideas. And actually, the mechanism is extremely simple. It's adiabatic evolution. And this is a picture that I guess everybody knows. If we have level crossing energies, the system, we evolve adiabatically. The system follows one of the adiabatic energies, which shows avoided crossing, and this is Landau-Zinner type of transition, and we have perfect, in the ideal adiabatic limit, perfect population transfer from 0 to 1. But if we have non-crossing energies, the quantum system will follow one of the dressed eigenvalues, and after little excursion to the excited state will go down to the ground state. So adiabatic evolution in this case means zero transition probability. And now if we have a laser pulse, and this is not detuning, but this is time actually. No, this is detuning. This is the spectral line. This is the adiabatic condition, and it shows that if the detuning is large, the adiabatic condition is satisfied. This is constant detuning. And here on the left and on the right, we are adiabatic. The only way we can transfer population from state 0 to 1 if we have no crossing is via non-adiabatic transition, and it's somewhere here in the middle. One analyzes the adiabatic condition, which is done here, and one finds that for the two basic types of pulses, one exponential and one polynomial, we have strikingly different features. For exponential, which is like Gaussian, hyperbolic secant, and so on, the half-width scales logarithmic with Rabi frequency. So there is power broadening, but it's logarithmic. But if you have polynomial behavior like Lorentzian, the half-width scales as omega 0 to negative number here, which actually is power narrowing. You increase the Rabi frequency and your half-width goes down. And this is very simple approach, actually, using simply the adiabatic condition. The very first my touch with experiments on power broadening was with the group of Klaus Bergman in Kaiserslautern in 20 years ago. This was two-photon excitation, and here the power, this is 2 photons, so the Rabi frequency is proportional to the power. The power increased from 0.75 gigawatts per square centimeter to 2.5 to 7.5, so the difference from the bottom to the top is 10 times in the Rabi frequency, but you see the line width went from 235 to 275. Actually, the increase is downwards. And we did power narrowing experiments on IBM Quantum, and this is actually the picture matrix that I'm going to explain what it is. This is the pulse shape. This was a Lorentzian, and this is truncated around the maximum, and then the truncation goes outside, and in this picture here we also almost have no truncation. No wings are truncated. And you see here typical power broadening. This is detuning, this is Rabi frequency. And when we move on, we start to see power narrowing. And here actually you see that we increase the Rabi frequency, and pi, 3 pi, 5 pi, 7 pi, 9 pi pulses. The more Rabi frequency you put, the narrower the line width gets, which I think was quite remarkable to confirm the theory. And we even had some sub-Lorentzian shapes, because if you have power dependence like this parameter lambda goes here in omega 0, and this is for Lorentzian squared, for Lorentzian to power 3/4, for Lorentzian to power 2/3. It should be, this power should be larger than 1/2, because at 1/2 you have infinite pulse area. And here the line width scales as omega to minus 1/3, so it's almost non-visible. Here it's inversely proportional to omega. You see pi pulse, and this is 9 pi pulse, so you see clearly the power narrowing. And for sub-Lorentzian, it goes even further. You see how this profile is squeezed. I'm finishing. And these are pictures, 1D against the detuning. You see the squeezing from pi pulse to 9 pi pulse. And this is the Rabi, the oscillations. The Rabi oscillations now decrease with increasing Rabi frequency, contrary to the rectangular pulse where they increase. Now they decrease, and you see that decrease is much more pronounced for sub-Lorentzian pulses than for Lorentzian and Lorentzian squared. With this, I would like to end and thank the people in blue which contributed to this work. These are the people in my group: 3 senior researchers, 1 postdoc, 4 PhD students, several master students, and these are our collaborators from abroad. We are very blessed to have many of them. And I would like to end by advertising a workshop we just finished at the Black Sea. Next one is going to be date which is very easy to remember, 20 to 24 of June. If you haven't been to Southeast Europe, in country other than Greece, this is a great opportunity to visit. It's a workshop which is between 40 and 50 people. Topics are very different. Like here we see different topics, which is great, because in specialized conferences you see the one and the same thing repeated all over again. So you're quite welcome to check and also contact me if you're interested to attend. Thank you very much.
So we have time for questions. Yes, please.
Nikolay, for your power narrowing, I was just wondering if you go to the sub-Lorentzian, more and more happens at the wings of the Lorentzians. So how sensitive is the whole thing to precisely have the form of your pulse in the wings?
If you can give me back the slide, I'll explain. Yes, this was fascinating, although it's not a precedent. Okay, here we are. You see here you cut a little bit from here. There is very little. This is actually 1.5% or something. This is 0.5%, and you see the difference between those pictures is quite substantial. So the wings really matter. A very weak excitation in the wing can make a difference. I actually have seen this before in femtosecond physics. There was great experiments reported in one of our workshops by Barry Brunner, where a very weak pre-pulse made a big difference then in the main excitation. So when you cut off your pulse, like here, this doesn't go unpunished, and you can really lose some great features if you're not careful enough.
Yes, please.
I'm trying to get a more intuitive understanding how this power narrowing happens. Do you fix the kind of interaction time?
Yes, we fix the interaction time. We only increase here. We increase the Rabi frequency.
And then, so if you go to the when the interaction time is fixed, then there's also the limitation due to uncertainty principle. Then the frequency resolution should be cannot be better than 1 over the interaction time, right?
It cannot be 0, sure.
Right. So how is it possible it can get narrower and narrower?
I don't think we are very close to the uncertainty principle here. I think this is still far away from it. But first of all, it's a curious feature to observe. There are actually some features that we don't quite understand, like this mustache feature. It shouldn't be there, but it is. These are experimental data. You can really squeeze it, but I think we are far away from the Heisenberg uncertainty still.
I see. Okay.
Actually, in theory, you should get a little more. I don't have the theory pictures. They are even more narrow. But we did all this because we wanted to know how the qubit, the superconducting qubit behaves, because we had long experience over the last 15 years with trapped ions, and we love them a lot. And I honestly believe that they are more scalable quantum computing platform than superconducting qubits, but we wanted to find out the intricate feature, how they respond to everything. And so far, it turns out they are quite quantum. But the problem with superconducting is that each one is different, and they are not connected as well as trapped ions. But we are still far away from this point.
I see. But ultimately, if we go to high power limit, will you go to the Heisenberg limit?
On paper, yes, but in theory, not.
All right. Thank you.